Alrighty. This is my explanation slash the correct answers and the corresponding justification for exam 2 for ECE 2000 or 20875. My name is Alex Isaac, and let us begin. So, for hopefully the setup looks clean. By the way, I'm going to be verbally explaining, and along with the verbal explanation, there should be I'll be sending a Word document that has basically all of my explanations in text for each question. So let's begin. Question 2.1, which is based off of confidence or based on confidence intervals. Question 1 is asking which of the following is the correct interpretation of the confidence interval we calculated. And the answer is we are 95% confident that the true population mean lies between 92 and 108 pounds. And I believe that is what I ended up picking. The explanation for which is for that is that the 95% says that 95% of experiments, like the one we just did, will include the true mean, but 5% won't. Another analogy for this would be, before I run the experiment, there's a 95% chance that the population mean will fall within the computed confidence interval. 2.2 is asking what must the population standard deviation that we were given, what must be the population standard deviation that we were given? And the answer for that is 20. How did I calculate that? Well, the standard deviation is obtained by dividing the length of the confidence interval by 3.92 and then multiplying by the square root of the sample size, which ends up being about 20.4. Hopefully this works. Let me go ahead. This would be the equation that you use. Hopefully you can see that well. Standard deviation, that's the equation I used. Alright, let's move on. 2.3 is asking which of the following is the closest estimate of the 99% confidence interval, and the answer should be 88, 112, which is what I ended up picking. And the equation for this is 95, actually let me see, let's see here. So the actual 99% confidence interval is closer to 84.7, 105.304. So I picked the next closest interval, which is about 88, 112. And the equation for that that I ended up using is here. Hopefully this will show up. Again, all of this will be in the hopefully this is visible here. The equations for all that I used are all going to be in the Word document that I have attached. This is the equation that I ended up using for 2.3. So let's continue moving along. 2.4 was a justification, which I already given, and in 2.5 it says suppose instead that we are not given. Let's see here. We are not given sigma. So to determine the 95% confidence interval, we calculate the sample standard deviation SS, or S, excuse me, which comes out to be the same as your answer for sigma in 2.2. So if we instead calculated the 95% confidence interval using this information, how would it change? Well, it would indeed become wider. And how did I find this? Well, in the equation for sample standard deviation, we have this, which is shown on the screen here in a second. This is the equation for sample standard deviation, where we divide by n minus 1. So in the equation for the confidence interval, we also divide by a smaller value, the square root of n minus 1, which gives us a bigger / wider interval. That is that justification. And now moving on to question 3. So it says for the regular expression shown here, would the string below be a valid match? And the answer is yes. The zero star at the beginning of the expression matches between 0 and unlimited times, or twice in this case. The 1, 2, 3 in brackets matches a single character present in the set, or 1 in this case. The next 3 sets of 0 through 9, match a single character present in the range of 0 through 9, or 0 to 9, excuse me, which covers the numbers 2, 3, and 4 in the test string. And the plus at the end is a quantifier which says to match one or more of the preceding token or value. And that all matches up. 3.2 is asking, so for the regular expression below, which is the same as above, would the string below be a valid match? And the answer for that is also yes. And it's for the same reasoning as I explained in 3.1. Every character within the string is present, every character within the string is present in the set specified in the regex. Yeah, same explanation as 3.1. 3.3 is asking for the regular expression, also the same as above, on 3.2 and 3.1. Would the string below be a valid match? And the answer is no. The answer is no, because of the 4 immediately after the 0, the string doesn't pass the match for a character in the range of 1, 2, 3. So it is because of this 0 here, the 4, which is out of the range of these specified in 1, 2, 3, that it actually fails. 3.4, for the regular expression, would the string below be a valid match? And the answer is yes. This regex has two groups. The first group, /D, matches a digit, \D, matches a digit equal to 0 through 9. The second group, D, matches any character that's not a digit equal to 0 through 9. 2, matches the same text as most recently matched by the second capturing group. /1 matches the same text as most recently matched by the first capturing group. So, in other words, it ends up actually copying the first group and the second group. And like I said, as I'm explaining, hopefully you can actually read as I'm talking, read along. Otherwise, following what I'm saying would probably be pretty difficult. So I apologize if what I'm saying is a little confusing without some visual context. But the answer is yes. The answer is yes. 3.5, for the regular expression, would the string below be a valid match? The answer is no. The first two groups don't pass, as group 1 expects a digit, but it receives a character, and group 2 expects a character, but it receives a digit. So the answer to 3.5 is no. 3.6, for the regular expression, would the string below be a valid match? No, it would not. The first two groups pass, but this time the /2 and the /1 both fail. /2 expects the same text as the most recently matched by the second group. It expects a character, right? But instead, it receives a digit. 4.1, what will be the print output of the following code? Oh, jumping a little ahead here. So, answer to 3.6 is no. And 3.7 is an explanation, which I've already given. So let's move on to 4, regular expressions part 2. So what will be the print output of the following code? The answer is hello, which is actually what I've chosen. In the code given, we're replacing the leftmost non-overlapping occurrences of the pattern hello in the string happy birthday. The set A through Z matches the uppercase character in both happy and birthday, hence why both are replaced with hello. The /W matches any character that is not a word character, hence why the exclamation is excluded. And I'm just going to really quickly confirm here that I'm still recording. Looks like I am. That is good news. Okie dokie. So yes, hello, which is what I have here for 4.1 is the correct answer. 4.2 is an explanation already given, which I've already given. 4.3, what will be the print output of the following code? The print output would be, this is an interesting one to spell. Let's see if I can, it's going to be over here. Well, that copies. It's going to be the option that I've chosen, which is ABC. C is the correct answer. This is what it should look like, which is what I have shown here. Let's see if I can move this over. There you go. Again, I'm pulling this from my Word doc that I have pulled up on my second monitor. This would be the correct answer. Ha 0y ha 0 o w 0 n. There you go. The regex above has a group which matches a single lowercase character, range A to Z. And following the first group, the /1 matches the same text as most recently matched by the first group, A to Z, lowercase a to z. Hence why we end up replacing only repeated characters with 0. And that explains the zeros that we see occurring here. So that's the answer to 4.3. 4.4 says, suppose we run the following code where A is a string defined beforehand. The printed output was Happy Halloween. So which of the following, which of A could have produced this output? And the answer is A is equal to R, and then /1/1/1 3 separate times. So as in the explanation for 4.3, the /1 matches the same text as most recently matched by the previous group. So with 3 /1s, we are looking for a character repeated twice, and replacing it with the same character repeated 3 times, which matches what we have in this case here for what we pass as Happy Halloween and what we have here. So that is the correct answer is A, B, C, D. 5.1, moving on here, bash now. 5.1 says command 1.sh has the following contents. Command 2.sh has the following contents, right? So we run the following on the command line, assuming all commands have execute permissions. So what will the contents of foo be, assuming that /n denotes, or \n denotes new line? The answer is \new line character 80 new line character, which is what we have here. This is actually the correct answer. When you run a shell script, we need to know what interpreter to use to execute the script. In this case, we're using bash itself, indicated by the !, exclamation, /user, /bin, /n, bash. The other line in command 1 and command 2.sh script is echo, which displays the line of text or string that is passed as an argument, and it prints it to the terminal. The line we run first sets A equal to 10, but does not establish A as a global variable. Export B equals 80 establishes B as a global variable. So when we execute the 2.sh scripts, only command 2.sh will be able to access B because B is a global variable, hence why only 80 is printed. Assuming bash, the bash variable V can be set to anything, which of the statements, moving ahead a little too quickly here. So yes, \n 80 \n new line character 80 new line character is the answer for 5.1. 5.2. The answer is, so assuming the bash variable V can be set to anything, which of the statements below, if any, are possible outputs of running the following bash command? The answers shown. Let's see if my answers line up here. Capital V, new line character, capital V, new line character. Yep, that's correct. And R, new line character, V, new line character, also correct. So these are the 2 correct answers, and the explanation is, for which is that the second command, echo capital V, so without the $, it narrows down our options immediately. Echo V without the $, prints whatever character follows the echo. In other words, only the character V can appear second in the output, which only occurs in the first and the third option. So those are our answers for 5.2. 5.4, because we're skipping 5.3, which is an explanation. Suppose command will generate an error when run. If we execute the following, what will the resulting contents of the file bar be? And the answer is world /n, which is C in this case. An important note to make is the function of the and operator, double ampersand operator, which works as a short circuit operator. It prevents dot / command from running until echo hello 2 executes properly. However, because dot command fails, bash stops trying to execute the two commands. On the other hand, the pipe operator, or double bar, the short circuit OR operator executes a command only if the previous command failed. So because the dot / command generates an error, the second command, echo world, arrow bar, executes properly and prints the word world prints the word world to bar. Tongue twister. Which is why C is the correct answer for 5.4. So 6, let's move on to regression part 1. This is part of the problem set right here, and 6 dot problem explanation. 6.1 is asking which of the following graphs would we most likely expect if we plotted the training if we plotted the training MSE and testing MSE as a function of the polynomial degree without any regularization. So if we use a higher degree of polynomials, we can reduce MSE. But this isn't always a good thing because drastically increasing the degree D can lead to overfitting / sacrificing the generalizability. Big word. The generalizability of the model. This will lead to a higher R² and low MSE on training data, but low R² and high MSE on testing data. So this is reflected most accurately in the second graph, right here. The second graph in which the test MSE increases drastically with degree D. So yes, the correct option is in fact B for 6.1. Skipping that, 6.2 to go to 6.3, we pick a degree D and find it obtained a very low error on the training data set, but very high error on the testing data set. Which of the following might help improve the generalizability of our model? Well, by regularizing the least square equations, which is the option C, ABC. Yes, option C is the correct one. So the generalizability of a model decreases due to overfitting, increasing the degree of a polynomial. So to counter overfitting and increase generalizability, we can use regularization, particularly of the least squares equations, to penalize non-zero model coefficients. This is done by changing the regularization parameter lambda. And that is why option C is the correct answer. Let's see how I'm doing on time here. Alright, looks like we're doing good on time. So 6.4, we pick D equals 2 and train a ridge regression model with some regularization parameter without regularizing the intercept. The result is y of x is equal to 10x squared minus 100x plus 1. If we'd instead not used any regularization, which of the following is a possible trained model, and the possible trained model, let's see here, the answer would be y of x is equal to 20x squared minus 120x plus 1, which is not, in fact, what I have here. It should actually be D, A, B, C, D. D should be the correct answer. So by regularization, we are mitigating overfitting by penalizing non-zero model coefficients. Because gamma is larger than 0, I know that the coefficients of y of x will not be different prior to regularization. Therefore, because regularization is reducing the coefficients and the y-intercept is unchanging, then the only possible choice is D, y equals 20x squared minus 120x plus 1. The coefficients are larger than the regularized model, and the y-int is the same. And one of the graphics that I used and that I should have put before I gave you the explanation, but I'll put it here anyways, is here. This is, I believe, from one of the lecture slides. And that is exactly what I used in my explanation, or the logic for which is based off of this. So let us continue to 7, making progress here. 7, so what type of statistical test should be used for this regression problem? Well, let's see here. Let us move. Uno momento. What type of statistical test? I believe. Uno momento. I have my Word document here. Just actually got a bit jumbled here. Looks like 6.1. 6.1. I apologize for this. Should have checked to see if this would not be messed up. Alright, fixed position on page. Perhaps I'll try to cut this out if I have time here. Let's see. Fixed position on the page. Okay, great. Alright, I apologize. 7.1. 7.1. What type of statistical test should we use? I say a two-sided t-test. That is actually what I said, two-sided t-test. We use a two-sided t-test because we don't know the standard error, sigma, and because our data set n is less than 30. That's the explanation for 7.1. 7.2, which of the following factors would decrease the p-value of the test? Well, a higher value of a. And so p must be less than alpha. Excuse me, I said A, I meant alpha. P must be less than alpha to be significant. And based on the alpha value, I can determine what standard deviation is. So therefore, by increasing the value of alpha, I can thereby decrease the p-value of the test. That is 7.2. So 7.2, the correct answer is actually A. I apologize. All of my answers are actually reflected in the Word document with the correct labels. So you don't only have to rely on my verbal confirmation of the answer. It should be in text as well. So yes, answer to 7.2 is A, higher value of alpha. 7.3, so repeat question 7.2 for the following choices. Which of the following factors would decrease the p-value of the test? Well, a higher variance of x1 through x20. So not A, actually B is the answer. The variance measures how spread out the data are about their mean. The variance is equal to the standard deviation squared. Therefore, as variance increases, z-score will decrease. So, by extension, as variance increases, the z-score decreases below 0, and p-value will begin decreasing. That is the explanation for 7.3. 7.4, we'll skip because I just gave the explanation. And 7.5 is asking, we conduct a test and find a p-value of p is equal to 0.00001, and which of the following, if any, can we reasonably conclude with high confidence? And actually, it should be two. We can conclude two things with high confidence. A doesn't equal 0. The feature does not have a non-zero weight, and y exhibits a dependency on x. So not A, it is actually B and C that are the correct answers. A small p, like 1 times 10 to the negative 5, indicates that I should reject the null hypothesis. This is strong evidence that the null hypothesis is invalid, that y is dependent on x, and that the feature model must therefore have coefficients greater than 0. So that is the explanation for 7.5. Moving on to 8, almost there. 8 is asking, 8.1 is asking, what is the feature matrix X we should construct to solve the equations? And actually, let me check here. Oh, we're still recording. Fantastic. What is the feature matrix X we should construct to solve the equations? The answer is A, B, C, D, E. Yes, E is the answer, where we have 4 columns and 3 rows. The columns being 1, 3, 4, 4, 2, 8, 8, 1, 11, and 1, 1, 1. And the explanation for this being that the feature matrix X, well, we defined it in class, or at least in the lecture slides. Don't think we were here for this lecture, or on campus for it. We defined the matrix X as being this. This is our matrix X, right? And this corresponds where we have the Y column here. The 1s correspond directly with what we have here. And this corresponds directly with the above selection of 1, 4, 8, 1. And also with 3, 2, 1, and 4, 8, 11. So I don't think I'm going to edit this video, so this is just all going to be in the video. Sorry there. Yeah, I was being shown a lizard. Sorry. Where was I? Yes, the feature matrix X. The answer is E, where this one right here. A, B, C, D, E. Yes. Okay. Great. Sorry about that. E is the answer for 8.1. Moving on to 8.2. 8.2, what is the target vector y? The answer is what I've selected, 9, 6, 21. The target vector y is a singular column consisting of the y variables in the provided 3 data points. In this case, the 3 y variables are 9, 6, and 21, which corresponds with B. 8.3, what are the resulting least squares equations? Well, the least squares equation is equivalent to, I'll put this image here for reference while I speak. The least squares equation is equivalent to what I have shown here, where we perform matrix multiplication on the feature matrix X and its transpose XT. Accordingly, the resulting least squares equations should equate to the option 4, which is 1, 2, 3, 4, which is what I have selected. Just to confirm, let me just make sure. I'm going to just put this also on the screen here while I... Oh, that didn't work. Yeah, answer is 4. I'm also going to try to paste that here. Let's see if that works too. There we go. Okay, perfect. This should be the correct answer because I know it's a little messed up here on the Chrome tab. That is the correct answer. Option A, B, C, D. A, B, C, D. D is the answer. All right, 8.4. Suppose we arrive at y hat is equal to 2x1 plus 3x2 plus 0x3 plus 1. And it says, what is the mean squared error on the training set? Well, the answer is 2.5, which is what I have. And I have had here, you'll see that I have actually a notebook pulled up. Or excuse me, not a notebook, but an Excel spreadsheet. And in it is where I actually do some Did I? Is this the actual notebook? Yes, it is. Haha. Good. I'm glad that I picked the right one here. I'll scooch a little bit over here to the left. It's kind of serving two purposes here. A couple questions around this Excel spreadsheet. But if we perform the following calculations, as shown in the table, we find that the mean squared error, or MSE, is 2.5. I will also include the spreadsheet in the email that I send. You can see some of the calculations. Bada bing, bada boom. Oop, escape, redo. And we find that once we sum the sum of squared errors, we get 2.5, which is our correct answer. A, B, C, D. D. All right, moving on. 9.1, we're getting there. So we obtain a new data point, 1113.7, for which we want to predict the value of y. What is the normalized version of this data point? The answer is 3, 6, and 1. 3, 6, 1. So using the following equation for standard normalization and the given standard deviations and means, I will put this image here. Here's the equation. There we go. So so based off of this equation, we find that the normalized version of the data point 1113.7 is 3, 6, 1, right? And that is just using the givens and plugging it in this equation. So that is why our correct answer is indeed B. 9.2, what is the predicted y hat of the example of the sample in 9.1? And the answer is 15. How did I find that? Well, by plugging in the normalized data point 3, 6, 1 into the equation for y hat, we get a value of 15. 9.3, we're skipping. Going to 9.4. Normalizing a feature matrix prior to model training accomplishes which of the following? And here we go. Let's see here. Well, the answer is it allows us to compare the coefficients in the trained model. Is that what I said? Yes, okay, yeah. So the answer is B. Answer is B. Again, my Word document here is a little funky. There we go. That looks a little bit better. Pretty sure. Yeah. Now, how did I calculate that? Well, if we, by normalizing the data before doing linear, yeah, okay, yeah. So 9.4, the answer is B. It allows us to compare the coefficients in the trained model, right? By normalizing the data before doing linear regression, we ensure that the coefficients are compared over a consistent range. That is the key. So that is 9.4. The answer to 10, which is n-grams in NLP, only 2 more questions. We're almost there. So we're considering this table here, right? This document word matrix, and it's saying, in 10.1, in which document or documents is the term frequency, TF, score, for the word data the highest? Well, let's actually take a look at a table I have pulled up here. Fixed position on the page. Hopefully that doesn't move anymore. 10.1, the answer is document A, not document B. It is document A. And we can take a look over here. We're looking for term frequency, and if I just go ahead and minimize this, I don't think I'll be needing it much anymore. We can always bring it back. If we come over here, here's our original table. And if we look at TF scores, we find that for data, the highest TF score is, in fact, with document A, which is actually 0.5. So it's not document B. If we go over to 10.2, which words have the highest inverse document frequency, IDF score? We see that, let's see, which words have the highest inverse document frequency, IDF score? Those words are Python and SAMI. Did I say that? No, I did not say that. I only said SAMI. Let's take a look at the table for justification. So our IDF scores are done here, the equation for which is, I believe I have an equation somewhere in my Word document that I can show. Bingo. These images just keep jumping around, Unfortunately, it looks like I do need to bring this back. If I do, boom, here's our equation for IDF. And for the heck of it, because I actually don't believe I showed the equation for TF, term frequency, I'm going to put that there too. So here are our 2 equations, term frequency and IDF. And those are these 2 equations that I applied in these tables. And we find that for 10.2, Python and SAMI are indeed, it's lagging a little bit here. Python and SAMI have the same IDF score and therefore are the answer. 10.3, which of the words have the lowest inverse document frequency? The word learning, actually, and that is what I selected, and it's based on the same equation and table I generated for IDF in 10.2. So based off of that table right here, same one that I used, I can conclude that learning has the lowest IDF score. It has a 0 IDF score. That's pretty low. 10.4. By the TF IDF measure, what is the most important word in document C? That word is SAMI, not dog. It is the last option here, SAMI. And it's actually based off of the below table, which is in the Word document, it's below, but in this presentation, it is over here. We're looking for the lowest TF IDF measure in the document C. And if you look over here, document C, the lowest. Ooh. Yep. Let me just make sure I'm looking at this right. Excuse me. We're not looking for the lowest. We're looking for the most significant word, right? In document C, and that actually happens to be rated at 0.225, which is the word SAMI. So that is actually why 10.4 is SAMI, not dog. Great. That should do it for the 10s. Let's move on to 11. Last one. So suppose we run the following code, and what would this last line here print out? This print b.x b.z. Well, the answer is 2 comma 36, or 236, no comma, just 2 space 36, right? Well, methods for a class take an extra self argument. The self argument refers to the object you invoke the method on. So after walking through the above script line by line, and by remembering that the line a.bar with 6 being passed to it changes z for both objects a and b, we find that 236 should be the output of the code, which is this correct answer here. 11.2. Suppose we run the following code. Will both the print statements in the code print the same result for all values of b? The answer is no. It is not. That is not the case. I did say yes here, but no. If you take a look, for values less than 0, the first print statement will always print the integer 5, which is actually defined here, that a less than 0. So, which was passed. So, for integer values less than 0, the first print statement will always print the integer 5, which was passed to simple objects here in this line. So the answer is no. 11.3, already gave an explanation. Let's move on to 11.4. What would be the printed output of the following code? And the answer is 15, because after setting the value o, lowercase o, to foobar with the value 10 passed to it, the value of o.x becomes 10, and the value of o.y becomes 5. So the value of o.y plus o.x should be 15, and that is exactly what gets printed out, 15. And for our last one here, 11.5, suppose bar is a class, and the following code will run without error. B is equal to bar 3, or with 3 being passed to it. Which method is a possible constructor for bar? Well, the answer is ABC. Def, init, self, comma a, and then pass. Well, methods for a class take an extra self argument. That is really key, because therefore when you pass 3 to the class bar, or to the method bar, you must include 2 arguments, one for self and one for the integer 3, or whatever integer you're passing. And that is the only 2 arguments are accepted in option C, which is why that is the correct answer. Alrighty, that is the end of my justification for the exam. Hopefully this covers everything. Hopefully I didn't ramble too much. And with that, I'm going to conclude the video, and hopefully this is good enough. Please let me know if you need any other documentation. I'll include the text justification in the email, as well as a link to the YouTube video. So thank you so much. Have a great evening or day, whatever time it is. Morning.
Oh, you can see me once.